Okay, so we're going to start with chapter 11. We're moving from the realm of concrete, finally, into the realm of steel. So we'll get into steel, how it's made, and do some of the structure of steel. I can't do, as with all the fluctuations in chapters, if you notice, chapter 11 is a rather thick chapter in comparison to, say, chapter 12, which is next week. So some of what is in chapter 11 will spill over into next week. And I'll talk about that at the beginning of next week, and then we'll do chapter 12. So it's a lighter load next week. We have 2 lectures before spring break, tonight and next week, and then it's spring break. And then I thought it was really unfair if I gave you a midterm after spring break. So you'll come back for a week, we'll do wood, and then after that will be the project 2 and the next midterm. So it just seemed unfair. In the old class layout, it worked better because spring break was later, so I could get you the midterm before spring break, and then you had the break where you didn't have to do anything. So I don't make the schedule, so it is what it is. What? I think so. It might be It's in 2 weeks. It's not this week. It's not next week. It's the week after, and I don't know the exact date. Is it the 26th? So that's the official spring break. I am very, very close to having all the exams graded. Those of you that visited me in my office noticed that I was frantically trying to input all your grades so that I can hand them back to you. I'm very hopeful that I can finish them during the break today, so I might make the break slightly longer so I can try to get those done because I want to get them back to you. So if I can finish them, we'll talk about them after the break. Okay? So let's start with chapter 11. In order to understand steel, we kind of have to start with the basics of what is steel, how did we get to steel, etc. So in order to understand steel, we have to take a step backwards into the realm of cast iron. Okay? And so cast iron was kind of the first steel-like material, right? It's kind of the precursor to steel, and we'll talk about what makes it different in a second. It's produced from iron ore in a blast furnace. Okay? It's very unpredictable in brittleness, and it's somewhere in the neighborhood of 3 to 4% carbon. Okay? How many of you have heard of cast iron before? Okay? What have you heard it related to? Drain pipes. Okay, that's good. Exhaust manifold with sewer pipes. Cookware. How about like a bathtub? Maybe an old bathtub is cast iron bathtub. Okay? So have you ever had an item that was cast iron break on you or crack on you? Okay, some people maybe yes, more people maybe no. So my best story that kind of illustrates cast iron and the fact that it's very unpredictable in its brittleness is we were doing a remodel where we had a cast iron bathtub from I'd say vintage 1961 or something. It was bright yellow, it was hideously ugly, right? It was built in, and we needed to gut the bathroom because we were going to do a jetted tub and all that kind of stuff in it. So it was wedged in with sheetrock and tile backer board and whatever, and we're like, you know what, this is going to be a really big pain to get out. Why don't we just break it into 2 pieces or break the corner off, right, the bottom corner, so we can lift it up and haul it out, recognizing it's really heavy. So, it's unpredictable, brittle, but, if I take a, sledgehammer to it, it should break, right? So being the macho guy that I am, I was like, okay, well, let's try this, right? So I got the sledgehammer out, and I must have whacked on that thing for a half hour. And it wouldn't break. It wouldn't crack, right? And so that's the idea of this unpredictable brittleness, right? If I had hit a different corner, right, different batch of cast iron, probably would have broken really easy, right? If you've ever worked with sewer pipes, the old cast iron sewer pipes, you have a couple of different ways to work with them, right? You can cut through them with some kind of a diamond blade, which obviously gives you a clean cut, or you can wrap a chain around them, right, and slowly cinch that chain, and it will actually break the pipe at that moment. Okay? So that concept of an unpredictable breaking point is kind of the key behind cast iron and should translate to why you wouldn't want to use it, right, in a building, because you don't really know when it's going to fail. Okay? So we needed a way of making something a little bit stronger than cast iron, right, so that we could use it in a building. Okay? So we worked through and we came up with what was called wrought iron, okay, which is taking, right, that same cast iron that we were using before, but we're purifying it. We're basically beating out the impurities, right, by beating it with a hammer, right? So the process of working the metal is causing the impurities to get out of it, okay? And it's very high cost because of the amount of labor that's required to do it, okay, because every piece has to be worked, by hand or by machine. It ends up being really high cost, which is why most of the time we're not going to see it, say, for a skyscraper. We're instead going to see it in a decorative railing, right? Someplace where you really want to see it, okay? Wrought iron has even less, right, carbon than most steel does now, right? So it's kind of at the very strong end of steel, okay? So we needed something that was somewhat in the middle. So along came the Bessemer process, right? And the idea behind this is that air is blown into this molten iron, right? And the process of having that air in there allows the molten iron to burn off the impurities. So to burn off those things that we don't want in it. And it allows us to produce a very large batch, right, of steel through this method because we can do a lot of it, and it takes about 20 minutes. So it's really fast to produce a lot of steel, right? Steel became very plentiful in the 1850s, right? And that's kind of when we started really seeing it a lot in the built environment, okay? So we've moved through cast iron into wrought iron. Finally, we're at steel. So what makes steel great? Okay, why do we care about it? Steel generally contains a range of alloys of iron that contain less than 2% carbon, right? If we're in the mild steel, right, this is what we would call ordinary structural steel, right? The stuff that this building is framed out of, the stuff that Trader Joe's is framed out of, the stuff that the AAA building is framed out of, right? A lot of buildings are made out of mild steel, right? And mild steel contains less than 0.3% carbon, right? So we went all the way from the cast iron realm at 3 to 4% carbon, right, all the way down to structural steel at 0.3% carbon. Okay, so we're really moving down in this strategy here. Okay, the amount of carbon, right, in a ferrous or iron-based material, right? Ferrous also refers to magnetic, right? Iron-based material determines the metal's property, right? If we have too much carbon, a la cast iron, right, pushing all the way up to there, it becomes very hard but very brittle and very unpredictable, right? If we have too little, right, we have a very malleable and weak iron. Okay, so it's this fine line of trying to identify how much, right, of that carbon is left in the steel or the iron. Okay, so steel whose properties have been optimized for structural purposes, right, is basically what steel is. So let's talk about how do we actually make steel, right? And we're moving into kind of the modern process for how I'm making steel. So the first step, step one, is that we need to smelt the iron ore, so the raw iron, right, into cast iron, right? And so this is produced in a blast furnace, and I'm going to show you a picture of that in just a second. It's alternating layers of the iron ore, which is kind of like dirt, right? It looks a lot like dirt, okay? It's alternating layers of that and what's called coke, which is just coal whose volatile components have been distilled out, leaving only that pure carbon that's going to burn. Okay, it's kind of the fuel for the fire, so to speak, right? And then crushed limestone. So let's move to the picture so we can see this a little bit. It's actually the next slide has a diagram of it, but this is what we're talking about. So those alternating layers go up in this vault. Okay, so the coke, right, the coal is burned with large amounts of air, right, forced into the bottom of the furnace, right? The air produces a carbon monoxide which reacts with the ore to produce elemental iron, okay? While the limestone forms what is called slag, right, which is basically stuff that you don't want. It's the extra stuff, right, but it collects the impurities, right, that are in with this process and allows you, the impurities attached to that slag and allows you to remove them out of the process. Okay, so the diagram helps, right? So this is inside that big thing that I was just showing you, okay? And so right up here we have our alternating layers, right? A coke layer, an iron ore layer, etc., right? We inject air in the bottom, right? And as that starts to burn, right, we burn off the impurities, we can take the iron ore out and start to work with it. Does that make sense? Right? And this is a very fast process, right? It burns quickly. So this is another example of one of those towers. Obviously, the tubes and stuff leading up to the top are to get the materials up toward the top, right? So this is inside a blast furnace. These are great pictures from Life magazine that we would never get in today, but it's fun to see them, right? And you got to love the fact that the guy's in here with short sleeves just like doing his thing, right? So safety things have changed a little bit since the 50s when these were shot, okay? So the liquid iron is drawn out of the bottom of the furnace, right, and sent on for processing into steel, right? And so the iron, step 3, the iron is converted into steel, usually by what is called the basic oxygen process, okay? And so the way this process works is that a hollow water-cooled lance, which is basically like a really long tube, right, is inserted down into the molten iron, right, and then it injects, next slide, right, a stream of really high-pressure oxygen, so just pure oxygen. But you guys all know from like classes in like elementary school, or I guess it would be middle school, where you'd like burn things and whatever. Maybe it was high school chemistry. I don't know. I don't remember, right? So when that happens, right, we need oxygen as part of the fire process, right? We need it to burn. So in doing so, when we're injecting that pure oxygen, it's going to burn off any of the excess carbon and any of the excess impurities that are in that, right? The other thing that's often added is a bit of lime and fluorospar, right? And that's reacting with those pieces, right? Those extra things that we don't want to form another slag of material that we don't want to get it out, right? It's giving them something to attach to, the impurities, right? So then finally, we're going to add any kind of new metallic elements that are going to alter the properties of the steel for a specific purpose. And we'll talk about what those extra additives might be and what they might do to the steel in just a second. Right? So this is the molten steel, right? This is inside a factory, right? It's a blooming mill. So they're transporting the steel inside these big vats, right, hung from above, and then they can pour them into these other vats to continue on with the process. Right? These are not pictures that I took. They're not ones that I've never been in one of these factories. I think it would be really fun to go, but I have never been in one. Right? So the entire process is very carefully done. There's a lot of laboratory testing and analysis to make sure that the impurities are at the levels they're supposed to be to give you the desired properties. The last thing that you want, right, is for this whole process to result in a bad batch of steel. Right? So we want the good steel when it comes out. The whole process from start to finish takes less than an hour. It's really quick. Right? Okay, so what are those additives that we might add into steel, and what do they do? Okay? If we add manganese to steel, it results in a resistance to impact. Right? So, for example, if we were using steel in a place like a stairwell, right, where it's forming the treads of a stair, right, where there's a lot of wear and tear, that might be a good use of this type of steel, right, because it's resistant to that wear. If we were using it someplace where there were two pieces of metal rubbing against each other for some reason, that would be a better use of this material because it's resistant to that abrasion. Right? If we add nickel and chromium to the steel, we get what's called stainless steel. How many people have heard of stainless steel before? Okay, my guess is you probably have, right? Stainless steel, the idea here is that we're increasing its corrosion resistance, number one, followed by its toughness and stiffness, right? Interesting thing about stainless steel is by adding the nickel and the chromium to the iron, basically, or to the steel, it loses its metallic properties, right? Which is why if you have a stainless steel refrigerator at home, it doesn't stick, the magnets don't stick to it, right? So no great, Hawaiian tropical palm trees on your fridge anymore, right? So stainless steel is great. We talked about back in the concrete section, if we needed steel that was resistant to rust, right, the rebar might be stainless steel, right? So this is what's actually being added to the rebar to produce that stainless steel, right? And stainless steel certainly comes in grades, right? So you might have something that's a really high-end stainless steel. It's not going to rust. It's not going to corrode at all. You might have something that's a lower-end stainless steel that if you leave it outside, pieces of it start to rust over time. Certainly not nearly as bad as something that was left untreated. So the other thing that we can do in terms of protecting steel from the elements, right? So one thing is we can make stainless steel, which naturally protects itself, right? The other thing that we can do is we can say, okay, I'm okay if my steel turns kind of rusty on purpose, right? And this is what's called weathering steel. And what happens is it develops a really tenacious oxide coating on the outside of the steel, basically a rust coating on the outside of the steel that then encapsulates the steel and protects the steel from rusting further, right? So it's meant to turn out like this, or it has this kind of rust color. That's the intent of it, okay? The brand name for this is Corten steel. You've probably heard of that before, and I'll show you an architectural example in just a second. So obviously we can use stainless steel, which I talked about. The last thing that we can do is galvanize the steel. People heard of galvanizing before? Right? We'll cover that more in depth when we get to the light steel, because all the light steel pieces are galvanized. But the idea here is this is significantly cheaper than these other options, right? But what we do is we coat the steel with a coating of zinc, basically. And the zinc, if you scratch it, corrodes on itself and heals the scratch, right? And so that's the theory behind the zinc as a coating, is that it sustains itself as a coating and keeps the material encapsulated, which makes it very valuable. Okay, it's not indefinite, but it's certainly something that works. So we have to show you an example, an architectural example, right? My 120ers are like, oh my God, we've seen this like 800 times, right? I love to show this example. This is by Takaharu and Yui Tezuka, and I will totally butcher, but it's the Museum of Natural Science, right? And anybody who can read Japanese might be able to pronounce that better than I can. But it's in Japan, and the entire outside skin of the building is built of Corten steel, right? So it's designed to naturally weather and naturally rust, which develops that color to the particular building, which is kind of a nice contrast to the landscape, too, certainly. Example of outside, right? This is obviously the glass window of one of the galleries. And this is looking up the tower. Now, if we look at this, right, you see these lines, these seams, right? Each of those is a separate sheet of this steel that's then been welded together on site. So one of the big advantages of steel, and we'll talk about this as the lecture goes on, is the fact that you can take separate pieces of steel, weld them together, and they become a monolithic whole. They become as if they were one continuous piece. Right? It's kind of like a pile. When we talked about driving a steel pile, you could weld on another section and keep going. Right? Same thing happens here, even though it's the outer skin of the building. So if we're going up this tower, right, all of these are seamless joints. There's no way for water to get in. Right? So it provides very good exterior cladding to this particular building. Okay? One of the very interesting things about this building is it's in a very heavy temperature, extreme climate. Right? And as a result of that extreme climate, it has a huge amount of expansion and contraction. Right? It's built out of steel, so when it gets cold, it shrinks. Right? When it gets hot, it expands. So the foundation for this particular building, and I really wish I had drawings of this, but I don't. And as far as I know, the architects who I actually had a studio with when I was in grad school have never released the structural drawings for this. But it's on kind of like a railroad car system on a track where one end of the building is fixed and the other end of the building is allowed to move backwards and forwards based on the expansion and contraction of the steel. So it's a very sophisticated foundation of this particular building. Right? So another view of this particular piece. Right? The fixed end is this end. The other end is the end that can move. Right? Looking at it from the outside. Now, depending on how much weather hits a particular piece of this Corten steel, this weathering steel, right, it's going to rust at different rates. So if we look at this particular example, right, the pieces that are under the window have a different color because they're not exposed to as much weather as the pieces that don't have the window. Right? So the top window is shedding water down and across and then down the sides. Right? Which is then shielding how much water is exposed to this particular piece. Does that make sense? Right? Which is why this is a brighter rust and that's a brighter rust than this. So if you as a designer think about this material and want to use it in one of your designs, you have to think of the fact that it's not a particularly clean material. Right? It's a material that's going to change. It's going to have this mottled appearance, right? As opposed to, say, a titanium or a stainless that's going to be very consistent, very sharp, and stay that way. Right? So you have to be okay with that. The other thing that happens that they did a really nice job in this particular building is there isn't any concrete or foundation that the rust can bleed down onto. Right? If you're using this kind of coating, right, the rust develops and the water then picks up some of the little bits of the rust stain, right? And when it comes down and hits the foundation, it's going to make a pool of rust-stained water, right? And that's then going to stain the concrete itself. So in this particular building, if we look down here at some of the outside positions, there's a distinct gap between the wall and what the outside patio would be so that you don't get that staining. So you really have to think about how you're going to deal with these particular pieces. In this example, right, this is one of the big doors that opens because it's a museum, gallery space. You got to be able to get large items in and out, right? So this obviously goes across. Recognize that the road is separate and independent from, right, the sides where you could get that staining. Another example, another couple pictures of it, right? And so this is what it looks like in the winter. So the extreme example, the extreme cold, right? That's part of why they had to work through that, right? That challenge with the foundation, etc. Right? But obviously, if you're designing in very different climates, and you have to know how your particular building materials respond to, right, these kinds of big climate changes. So, in terms of the structural steel we actually use, so we talked about how to produce steel from iron ore, right, to go all the way from the stuff you mine out of the ground, right? But how do we get most of our structural steel today, right? We get it from scrap cars, scary as that is, right? But if we're thinking about it, that could be a good thing, right? So instead of throwing these cars away, we're actually using them and being able to reuse them or recycle them, right, for later. So this is kind of an interesting topic in sustainability, right? So they're produced by what are called mini mills, right, using an electric arc furnace to melt the steel down, right, which then they can reuse, right? Mini mills is nowhere near the thing that you could like, oh, it's so small you could put it in the back of your pickup truck, right? A mini mill is actually really large. So just because it's called mini, don't think small size, right? A mini mill can consume up to 300,000 cars per year, right? That's a lot of cars, okay? The truth is, a lot of what we do with steel, and we're going off, we'll continue with this for a second. For example, right? You crash your car here, okay? The insurance company decides, you know what, you're done, you totaled it, it's over, here's your check, we take the car, right? They then sell the car to a steel recycler, right? Obviously, they strip off what they can and sell off. They sell the car to a steel recycler. Chances are the steel recycler, and there's a good example of this in downtown Oakland that does this, will grind up the car into a whole bunch of little tiny pieces, right? And you've probably seen on the road, right, a truck that looks something like this with the smashed up cars, right, going toward Oakland, where they're going to be ground up into little tiny pieces, right? They take all those little tiny pieces, they put them in a container, and they put them on a ship, and they ship all those little tiny pieces to China, right? China then uses these mini mills, melts the cars down, produces nice quality steel, right? Then ships it back to us, and we pay for their steel that we ended up giving them cheaper, right? And it comes back to us. So it's kind of ridiculous. The other big thing that was happening in the steel industry is that China is doing so much building that they're actually consuming the bulk of the steel that's available right now, right? Which is part of why the price of steel has gone up. Yes, sir. What? Which dam? Three Gorges. That's the biggest dam project the world's ever seen, and they took up some of the 9/11 steel. Yeah. So it's very interesting that we're recycling this stuff. So certainly it doesn't have to come from the scrap cars. It could come from the Twin Towers, for example. The point is, if steel's out there, it's worth recycling, right? There's a reason that all of us have curbside stuff to recycle steel because it's very usable, right? We do. There's some environmental issues with them that we might be slightly more strict about than other places. I was actually down in Peru. I don't know, a long time ago, and where we were staying was remarkably close to a steel mill, and it was one of these like mini mills, and it was actually creepy because you'd go out at night and there was this glow from the furnace that was just like permeating around, right? Large amounts of smoke and steam coming off all the time, changed the temperature of the water in the ocean nearby because they use the ocean as part of the cooling. So it's kind of a little bit of an environmental issue, right? Which is the other thing that we should think about when we talk about sustainability, right? So steel could be determined or could be called something that is very sustainable, right? We're recycling scrap cars. That's a good thing. We're recycling steel out of buildings that have been torn down. That's a good thing, right? But on the other hand, the amount of energy it takes to actually melt those things down and produce new steel is incredible, right? So you could argue either way. It's sustainable because we're recycling something, right? But on the other hand, it takes so much energy to make the steel back into something that we can use, right? So it's just kind of a toss-up. But that's why I don't think there are too many of the mini mills. There are certainly mini mills in the United States, right? But it's not as common as somewhere like China where the environmental standards are a little bit looser. We never covered that slide. Let's go back to this, right? So steel shapes, right? Mini mill melts all that steel down. How do we get the shapes out? Okay? So after the steel is made, whether it's made from scratch or whether it's made from recycled cars, it's cast into beam blanks or blooms, right? Which are basically thick approximations of whatever the final shape you want is, right? So if we're doing a wide flange, it's going to be in roughly an H shape, right? If we're doing some kind of a flat sheet, it's going to be a larger flat sheet. It's going to be a rough size, right? The beam blanks are then reheated as necessary and passed through a successive series of rollers, right, that make it closer and closer to its final shape, right? Eventually, basically getting to the final shape. Okay? So here's an example of rolling this into its final shape, right? Recognize that it's pretty flexible in the process, right? This is an example of the rollers, right? They're working to produce this wide flange here, right? There are little jets of water that are helping to cool it and control the temperature a little bit as it's coming through a particular factory. Another example of a factory, you can see a lot of the production happening by the stripes of color, right? And so those are various examples of kind of getting this process through, right? The finished shape is continuous until it's cut into shorter segments by what's called a hot saw, right? And the reason it's called a hot saw is the steel's still hot when it's cut. Okay? The segments then go on to a cooling bed where they're going to cool down in a controlled environment, right? And then eventually a straightener might go along and correct for any kind of crookedness or something that might have happened during the cooling process, right? To keep them nice and consistent, right? So this is an example of a hot saw, small piece of steel, right, coming through. It's a wide flange. The hot saw is cutting it into the desired length pieces, right? Most of the time, the desired length pieces have something to do with where it's being transported or what it's being made into, right? Recognize that if you're transporting something on a ship or a barge, it can be a much longer piece. If you're transporting something on a truck, it needs to be a shorter piece, right? And that's how we kind of determine what the sizes are. We're continuing here by rolling our steel into its final shape, right? An example of inside of one of the sets of rollers, right, where the steel passes through. These rollers tend to be adjustable, right, so we can get different thicknesses, we can get different shapes out of them, depending on what the steel manufacturer is trying to do. Another example of rolling steel into final shape. This is not the best example because it's cold rolling steel, not hot rolling steel, and we'll talk about the difference in a second. So, if we're going to talk about steel shapes, and this is something that I can tell you right now will show up on a test, I promise, right? We have to understand what the designations mean and what these shapes are, right? And how do we determine what size they are, right? So, we have a designation, right? W blank by blank. So, for example, W21 by 83, right? What's that telling us? The W stands for the fact that it's a wide flange shape, right? And a lot of you may look at this and say, wait a minute, isn't this an I-beam? Okay? And the world of I-beams has transitioned a bit in the steel industry. I-beams were hugely used, right, up until probably the mid-'80s or so, right? Then they started to get phased out and replaced with what are called wide flanges, which are basically the same shape, but the flanges here and here have become a lot thicker, right? And that's for structural reasons, primarily driven by the earthquake territory, right? So we're moving into the wide flange. The other thing is the width of the flanges has been getting longer, right? So in the old thing, an I-beam might look something more like this, right? And now a wide flange is going to look more like that, right? So we're changing from this shape into this shape. This is a much structurally stronger shape. Yes, sir? Oh, they're transitioning to S-beams? Okay, that's good. I'm glad you're adding things. I appreciate it. So, anyway, back to the wide flange. The book doesn't mention S-beams in it, so it won't show up on a test. So, W is the wide flange designation, right? The second part, so this first number here, right, is the depth of the beam in inches, and it's the nominal depth. And we'll talk about nominal measurements a bit more when we get to wood, right? But the depth is from flange to flange, right? And then the last number, so by, the last number is the number, right, of the weight in pounds per lineal foot. So for each foot of the beam, how much does the beam weigh, right? So if you had, let's make the number simple, right? Let's say you had a W 21 by 100, okay? It's 100 pounds per lineal foot, okay? So if we have a beam that's 1 foot long, it's 100 pounds. If we have a beam that's 2 feet long, it's 200 pounds, right? 3 feet long, 300 pounds, you get the idea, right? 10 feet long, 1,000 pounds. 20 feet long, 2,000 pounds, right? So that's an easy way of doing the math, but, and I'll cheat a little bit ahead because we're going to go through all of them. If it's ever, right, W blank by blank or something else, blank by blank, it's always going to be depth followed by weight in pounds per foot, okay? If it's 3 numbers, it's going to be different, which we'll talk about in a second. So wide flange depths are going to range from 4 inches to 18 inches in 2-inch increments. So 4, 6, 8, right? Then we're going to go from 18 to 36 in 3-inch increments. And then from 36 to 44 in 4-inch increments, which basically means you have 40 and 44, right? So our standard wide flanges are going to go all the way up to 44 inches in depth, right? All the way from 4 inches. So there's a pretty good range, right? So let's test that, okay? A W10 by 112 has a depth of 10 inches. Good. And a W10 by 122 has a weight of 122 pounds per lineal foot. Okay? Everybody understand the pounds per lineal foot analogy? Yes? I'm hearing a no from somewhere. No. Okay. So let's see if we can explain this again, right? So if we're measuring a beam, right? So let's say we have one of these beams and it's 10 feet long. Okay? If we have a number that says pounds per lineal foot, and so this one's 112, but let's round down to 100 to make it easier in our heads, right? And it's 10 feet long. For every 1 foot that we have of beam, that beam weighs 100 pounds. So if we have 10 feet, right, we multiply 10 by the 100 pounds per foot of the beam, we end up with the overall beam weighing 100 or 1,000 pounds. Does that help? Okay. If it doesn't, let's talk after. Okay? Okay. So we move on into a different shape. This is HSS, which is hollow structural section steel, right? It can be square, it can be rectangular, it can be round, or it can be elliptical, right? The most common is square or rectangular, right? But depending on what you're trying to make, it could vary, right? So notice we have something different. We have the HSS designation, so we understand that it's going to be a rectangle. We have 3 numbers instead of 2, right? So if we have 3 numbers, it's going to tell us something entirely different. The first number, right, is going to be the width. Second number is going to be the depth, or in this case, they're calling it the size, right? It doesn't really matter which order they're in, right? One side, the other side, okay? The last number is going to be the thickness of the wall of this particular piece, right? So it's a different way of measuring this. So instead of having pounds per lineal foot, we're going to have a thickness of a wall. So we have 3 measurements. It's always going to be one side followed by the other side followed by the thickness of the wall, right? So if we have square or rectangular shapes, 1 inch to 48 inches in thickness, or 1 inch to 48 inches to a side, right? And our thickness is going to be anywhere from 1/8 of an inch to 5/8 of an inch, right? So if we have a really big column in a building, that steel is going to be 5/8 of an inch thick, right? If we have some kind of a little small piece that's going to, say, be the leg of a table, right? It could have something as thin as 1/8 of an inch to the wall, right? If we have an oval shape, it's going to be slightly different in its size. So let's test ourselves. HSS 10 by 8 by half has sides of 10 inches and 8 inches, right? Has a thickness of 1/2 inch. Okay, so this should start to make more sense as we move forward. Okay, we have what's called a channel section, right? And this one, for whatever reason, they're calling the depth, right, across the bottom. Imagine the channel section standing up. Somehow that's easier to see it. I don't know why the image isn't rotated, but it is what it is. So C is the American Standard Channel, right, designation. We have two numbers. That's telling us that the first number, right, is going to be the depth in inches. The second number is going to be the weight in pounds per lineal foot. Right? And part of the reason that these designations change, is that it's not a consistent thickness, right, between here and between here. If we go all the way back to the wide flange, the flanges aren't as thick as the web. Right? So it's going to vary, and that's part of why we have a pounds per lineal foot measurement instead of something that was C blank by blank by blank by blank by blank. Right? It's too much information. If we have pounds per lineal foot, we understand how strong that particular piece would be. Right? Has a bunch of nominal depths of sizes. I'm not going to ask you to memorize something like, does a channel have a 9-inch depth? I don't really care. Right? You can look this stuff up. I just want you to know what a channel is. So if you saw a C blank or C, whatever it is, well, let's do it. Right? A C 10 by 30 has a depth of 10 inches and has a weight of 30 pounds per lineal foot. Does this kind of make sense? It's repeating itself a little bit. Right? An angle. Okay, L would be the symbol for angle. It looks an awful lot like an angle, so it shouldn't be hard to determine that it's an angle. The first two numbers are the nominal depths of the two sides, right? Followed by the third number, which is the thickness of the legs, or the thickness of the sides. Right? So we've got a variety of side pieces. These are less commonly used as like columns or something. They're more likely to be ledgers or something that's going to support a brick window opening or something like that, right? And they're going to have thicknesses from 1/8 of an inch all the way up to 1 inch and 3/8. So, testing that knowledge again, L 6 by 5 by half has sides of 6 and 5, right? A 6 by 5 and by half has a thickness of 1/2 inch. Okay, I think you guys got it now. Okay. So, we talked so far entirely about hot-rolled steel and hot-worked steel. Okay? There's another type of steel, right, where we produce the rough shape hot, we allow that shape to cool, and then we transform that piece of steel into something different at room temperature. Right? And that's what's called cold-worked steel. The steel is much stronger if it's cold-worked than if it's hot-worked because it's actually realigning the crystalline structure of the steel in the process, right? So you can think of like folding something, right, as increasing its strength. So light gauge steel, sheet steel, right, is often folded into sections, right, that might allow it to span greater distances, right? I have examples of light gauge steel, which we'll talk, more about, but it's something like this. This is actually aluminum, but you get the idea, right? It's bent into shape. Here, this better example, right? So this particular piece is flat to begin with, right? Cold at room temperature, these edges are folded up, and that adds to the strength of this piece of steel, right? And if I'll pass this around, this is actually a remarkably strong piece of steel for how thin it is, right? And so this is what we refer to a lot as light gauge steel construction. We'll spend all of next class talking about light gauge steel, but we're covering the process of how it's made right now. Okay, it's great for spanning really short distances and small walls and that sort of thing, which is where it's commonly used. Heavier plate stock can also be folded and then welded together to form the hollow structural steel sections. Right? So we know that the thickness is much higher on those steel sections. Right, the HSS, you guys remember the rectangles, right? What happens is you take a flat sheet, right, and mechanically, while it's cold, you fold that steel together, right? After you fold it together, a machine will come and weld the joint of those two folded pieces together. And that's part of what makes it an extremely strong column for a building, right? So it's especially good for twisting torsional or twisting stresses and buckling. Great reason to use it as a column. It's not the only reason to use it, right? But a lot of times that's why it's used, right? That's why it's a lot in trusses as well as columns. And the steel can also be cold drawn, right, through dies to produce extremely high-strength steel cables, right? And those are the types of cables that we're going to use in either pre-stressing or post-stressing concrete, right? We're going to be using them for suspension, like the Bay Bridge, for example, right? These are the types of steel cables that we're going to use for that. Okay? So we're going to take our break now. It's a little bit early, and I'm going to say let's go 25 minutes, right? Because I want to try to get all your tests done and give them back to you, right? So we'll come back at 7:40. Okay.